So now we will have the first short course of the meeting. It's Miguel Zilhão. He's an investigator in Navarro University, and he's probably one of the, I'd like to say, leading experts in numerical relativity. And he's going to talk about numerical relativity and the Einstein toolkit. So, please.
Thank you very much. Can you all hear me? Yeah, it's working? I'm going to assume so. Okay, so first of all, thank you very much for having me. It's very nice to be back here. As I've already been discussing with Professor Crispino, this is the second time that I'm here. The first time that I was here was 12 years ago. I was a PhD student at the time, so I was just about to finish my PhD on this very topic, and it's really, really nice to be back. So, yeah, the goal for this session, so this will be the first day, is to sort of motivate a little bit and the topic itself of numerical relativity, and to go a little bit further, in particular in this framework, in this tool that I use, and it's one of the most widely used tools for this field of numerical relativity, which is the Einstein toolkit. So it will be this set of lectures will be a little bit more technical than what I would usually present for a standard talk, let's say, because it's really the idea of it being a mini course, right? So there will be some more technical parts, and then there will be a hands-on session, which I'm not sure if it will start tomorrow, but if it doesn't start tomorrow, it will definitely start on Wednesday. Now, for that, it's actually, so for those that would like to follow along in your own machines, what I'll be saying, what I'll be describing, it's very important that you download this VirtualBox image. Okay, so so this QR code is for that image. So I had made available a link before, but I then realized that the link was not properly working, so I made a new one, and this is the link for that. So for those who are interested in following along, please download this. It may take a bit because it's like 7 gigabytes or something like this. So it's important that you do this beforehand, right? Because then tomorrow or Wednesday, I'll assume that everyone that's interested will already have this, and we'll start immediately, okay? I'll repeat this. I'm not sure if we'll be able to start tomorrow, so I'll repeat this again tomorrow. But just in case, again, for those that are interested in following along with your own machines, please download this image beforehand. Okay, but before that, let's first go through the theory part. And the theory is numerical relativity. Now, I actually already talked a little bit about this last week in the outreach, in the Nastro session, whenever that was last Wednesday, right? So that was last Wednesday. Some things will be repeated, and other things will be, and then on some topics, we'll go a little bit more in depth. So let me start with some basic definitions, right? So I usually choose to define numerical relativity this way. Of course, I mean, some people may disagree, but I think this is a fair way to define this topic, this field. So it's essentially about solving numerically the full general relativity equation, so the full Einstein equations. And this is typically done for dynamical spacetimes in the strong field regime where no approximations hold. And thus, we resort to numerical methods. The goal is to understand gravity in its nonlinear glory. And there are a few challenges, this is actually not a completely trivial problem, but these days we have a fairly good understanding of it, and this is what I will be telling you about. Now, the motivation for the development of this area, of this field, if you want, historically came from gravitational waves, the field of gravitational radiation, so astrophysics, gravitational wave astronomy. But interestingly, this is something. So this is an area that found applications not only in this regime, but in a much more broader, wider field. So within topics within mathematical and theoretical, more mathematical and theoretical, such as studies of the cosmic censorship hypothesis, stability of black hole solutions, for instance, studies of black hole interiors. This is finding applications also in high energy particle systems through the ADS-CFT correspondence. There are applications also, I haven't included here in this list, but there are applications also for cosmology. So yeah, it's a very, it's a set of tools that finds applications in a very broad spectrum. So I have here a slide of some brief, very, very brief history and some important milestones. I'm not going to go in detail also because we're running a little bit short on time, but I would just like to point to two important, or a couple of things that I think are very telling. And the first is this very first one, which is the 1915. This is when Einstein's equations were published by Einstein, as we should all know. And so 50 years later, which more or less coincides with around the time where computers, I mean mainframes, started to become available to universities, to institutions. That's more or less when it coincides with the first documented attempts at numerical simulations, right? This was 50 years after the equations were first published, but it was more or less when researchers could actually do it, when computers were available, right? Now, this is the 60s, right? So in 64, however, again, it was only 50 years later that actually the first simulations of black hole binaries, so the two-body problem in general relativity, was actually accomplished, right? So this was something that took 50 years for a variety of reasons to be done properly, okay? And in a way, it was sort of falling behind other fields that also rely on computational infrastructure, like, for instance, computational fluid dynamics. I mean, there's already, from the 70s, 80s onwards, there are already lots of important results in computational fluid dynamics and other such fields. However, for numerical relativity, even though there were very important results during the 90s, this one in particular, so the discovery by Chopik of critical phenomena and gravitational collapse, what was considered to be really the holy grail, a simulation of a black hole binary, so again, the two-body problem, it was proving really difficult to tackle, and it was only in 2005 with the simulations of Franz Pretorius, and then in 2006 with what are called the moving puncture simulations by two groups that really marked what people call now the breakthroughs in the field. Okay, so let me go a little bit through the formalism of this field. So we start off with Einstein's equation. I trust that most people have seen these equations. We like them very much. They are very elegant. They're very beautiful. However, they are also a little bit misleading, right? Because hidden here in this elegant way of writing the equations for gravity, this is what's actually hidden, right? I mean, if we expand the equations out, what we get is something like this. So this is a set of 10 coupled, second order, nonlinear partial differential equations. So it's really not easy to tackle, even though we know of quite a few exact solutions. Typically, we can only find such exact solutions in cases where we have a lot of symmetry assumptions, for instance, like spherical symmetry, time invariance, and so on and so forth. The general case, I mean, for the general case, the equations look like this. So of course, we need to be a bit smarter in how we tackle these equations, in particular, if we want to give them to a computer and get something meaningful out of that. There are a couple of well, more than a couple. There are a few different ways to do this. One that's popular. I don't want to. Yeah, I should probably skip this. But anyway, let me try to go through this fast. One approach is what is called the harmonic gauge or the generalized harmonic gauge. And the idea goes as follows. So we start by writing Einstein's equations like this. So this is the trace reversed form of Einstein's equations. And then we impose that coordinates are harmonic. So here we are using to our advantage the fact that, well, we have coordinate freedom in GR. We have a lot of gauge freedom. And we're making this choice. So we're choosing a coordinate system where the coordinates are harmonic. What do we mean by harmonic? We mean this. So we impose. So we define these quantities H, and we promote them to independently evolved variables. Now, if we do this and we expand out Einstein's equations with this assumption, then the Einstein equations, they take this form. Now, this may still look very complicated, but we have dramatically simplified our problem. And let me show you why. Because what we have is essentially a set of second-order wave equations for each component of the space-time metric, right? So we have here essentially the D'Alembert operator acting on each component of the space-time metric. And this is equal to, well, a bunch of source terms, okay? Now, this is really, really nice because this set of equations have very nice properties, in particular that they are symmetric hyperbolic, and this was what was used in particular for the very first simulations of orbiting black holes that I was telling you about, so that were used in Franz Pretorius 2005 breakthrough simulations. Now, this is not the approach that I will be focusing on. We'll be focusing on what is known as the 3+1 decomposition, which follows a different approach. And the approach is as follows. So I'll just give you the very abridged story, but please check this really nice review by Eric Orgouillon if you really want to delve into this and to know all the details. The idea is the following. So we start by considering a set of hypersurfaces sigma that are covering our manifold M, right? So we're starting up with some manifold. We're making no assumptions of symmetry. We're just going to foliate this with this set of hypersurfaces, okay? Sorry, there we go. And then, so from here, we define what we call the Eulerian observer, and we define the induced metric or 3 metric on each of these hypersurfaces and the extrinsic curvature object, which is this. So let me go back. Sorry, yeah. So basically, what are we doing? So we're defining for each of these 3 hypersurfaces here, so one here, the other one there, the other one there, etc. So each of these hypersurfaces, they are 3-dimensional quantities. Each of these will have their own intrinsic 3-dimensional metric. And they're evolving in this manifold, in this 4-dimensional manifold. So they're embedded in this 4-dimensional manifold in some way, and this is described by the extrinsic curvature. This is just basic differential geometry. So these are these objects here that we are defining. So the induced metric on the metric of each hypersurface, and the extrinsic curvature that basically tells us about how each of these objects, each of these metrics, is embedded in the higher dimensional in the 4-dimensional manifold. Okay. Now with this, what we do is we do projections of Einstein's equations. So there are 3 projections that we can do. Again, this is all in the language of differential geometry. So first we can do a full projection onto, so we can take Einstein's equations, which are written here again in the trace reversed form, and we can act on the left side and on the left-hand side and on the right-hand side with this projection operator. So basically, we are projecting the equations onto the hypersurface, each hypersurface sigma. Okay, so this is one projection that we can do. We can also do a projection totally perpendicular to sigma, so we can act with the normal vector, and then we are left with this again after a lengthy differential geometry computation. And we can also do a mixed projection, so we can act with this projector here, which is the mixed projector. So partly we're projecting on the hypersurface, and partly onto the normal vector, and we are left with this. Now, with this and writing the metric in the four-dimensional metric in this form, now again here we're not making any assumptions of symmetry or of sphericity or Killing vectors. This is fully general. It's just a particular ansatz, particular way in which we can always write our metric element. So if we do that, and using these equations that I was just showing you, what we end up with is this set of equations, which are known as the ADM-York equations. And again, now now we've drastically simplified our problem once again, right? So we no longer have that mess of a system that I was showing you in one of the first slides, right? So this is something that we can tackle, and in particular, this is something that we know how to give to a computer. Now, for those of you that may be seeing this for the very first time, I just want to point out that you've seen a similar set of equations. You've for sure seen a similar set of equations before, and these are known as the Maxwell equations, right? So everyone is, I hope, has seen these equations. These are Maxwell's equations. And, I mean, modulo some important differences, but the structure of these equations is the same as these ones here. And let me point out the similarities. So we have a set of evolution equations. What is this? So this is a set of equations that have explicit time dependence here, okay? So this is something that I can use to march a state vector forward in time, right? In particular, if I give this to a computer, okay? And I also have a set of constraints. So these are this set of equations has no time dependence. So these are equations that need to obey at every time level, but are not used to march the equations forward in time. And this is exactly the same that we have in electromagnetism. We have a set of evolution equations. So these two equations here, this is what tells us how the electric field and the magnetic field march forward in time, given their profile at a particular time. And these equations here, so the divergence of the electric field and of the magnetic field, these do not have any time dependence. So these are a set of constraints. So if we are solving Maxwell's equations, these two, they need to be obeyed at all times. Okay. So in a way, so this is the similarity between these two systems. Now, of course, I mean, that's more or less where the similarities stop, right? I mean, other than this, they are very different in the sense that, so Maxwell's equations, as we know, are linear equations, and in particular, if we have two solutions of Maxwell's equations, if we add them up, we still have a solution. I mean, this is what being a linear set of equations means. The Einstein's equations, on the other hand, or the ADM-York equations, are nonlinear. So if we have two solutions and we add them up, we no longer have a solution. Okay? But anyway, the structure of the equations is similar, so I think it's something that's instructive to have in mind whenever we look at a system like this. Now, I won't be going into a lot of details about this, but I should point out that in practice, the system that I just showed you is not the one that's used in practice for evolutions of Einstein's equations. So a more complicated system is used, which is typically known as the BSSN equations or similar systems. I'm not going to go into the details. I just wanted to, well, to show them because this is important, and also to point out that it's sort of, I mean, the rationale is the same. So we still have a bunch of, we have more, but we still have a bunch of evolution equations that we can give to the computer, and the computer knows how to, so that the computer knows how to march these equations forward in time. Okay, so now, if we want to do time evolutions, if we want to do numerical simulations of any given system, then the very first, or one of the very first questions that we need to address is how to set up the initial data. So what does this mean? Well, it means that we need to be able to properly set up our physical system in a way that, well, so we need to set up our mathematical equations in a way that's representing the physical system that we want to be evolving. And in particular, we need to solve the constraint equations that I was just showing you. I mean, this is exactly the same as in the case of Maxwell. So if you want to evolve Maxwell equations, well, we better be sure that what we're evolving, what we're calling a magnetic field, is something that it's diversionless, right? And we better be sure that what we're calling the electric field is something that, if you take the divergence of it, is your charge density, right? So this is what solving the constraint equations means. And here we have, so here in GR, we have a similar problem. We need to solve, so we need to set up our state vector. We need to set up our evolved variables in a way that represents our physical system. And in particular, it needs to obey this constraint equation. So it needs to obey these two equations. In general, this is a very, very non-trivial problem. These are coupled nonlinear elliptic equations. So yeah, it's really quite a non-trivial thing to do generically. But there are some situations where this actually has, well, simplifies considerably. One such example is if we are happy with momentarily static initial data. So this would represent, for instance, two black holes momentarily at rest, okay, at a given, I mean, for whatever reason, we would have a system that evolves in such a way that just finds itself on a particular, at a particular time, momentarily at rest, and then we want to evolve it from here. It's not particularly physically meaningful in many regards, but in many situations, it's an extremely good approximation. So it's the equivalent of just, you know, starting with two black holes and just they're at rest. You let them evolve, so you sort of let them go, and then they will just fall onto each other in a head-on collision. And this is actually quite simple to set up. So this is a momentarily static configuration. So the extrinsic curvature, which here we can think of it as the conjugated momentum, is 0. We are considering a case of no sources, so vacuum GR. And in such a case, then we can solve these equations that I was just showing you in this way. This was actually done first back in the 60s, right? This is what is known as the Brill-Lindquist solution. This solution this method was found at a time where the term for black hole hadn't even been coined, right? So this was in this paper here. These were known as wormholes. But anyway, so the point here is that such a configuration, this is known. This approach is known how to tackle, and it actually works quite well in practice for many situations. Okay, so I'm going now to 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 move ahead and just pretend that we now have all the technical infrastructure that that we need in order to solve to do this sort of evolution. I mean, there are many technical aspects that need to be taken into consideration. I will go back to them. So I'll go back to at least to some of them. Well, depending on how, or maybe even today, but if not today, in the next during the next sessions. But first, let me just show you a few of the applications, a few things that you can do, assuming that you have all this infrastructure working. Some of them actually were already mentioned by Carlos just now. But so, for instance, of course, the first paradigmatic example that one can do with this infrastructure is our black hole collisions. And so here I'm showing you such an evolution. So this is something that is performed with the Einstein toolkit, which is what we will be covering in the next in the next few days. So I would just like to point out a couple of things. So this is really well, with the infrastructure, this is actually quite simple to do. The whole infrastructure that you need in order to evolve such a configuration is fully provided with the toolkit itself. So which is something that's free and open source. So if you just download and install the toolkit, which is well, we won't go into those details, but we can cover a little bit of that in the next during the next sessions. But yeah, this is something that you can immediately do on your laptop. Now I'm just trying to find my mouse. Yeah, it's lost somewhere. I wanted to play this again. Ah, there we go. Okay, there we go. So just to say a couple of things more about the simulation. So what we're seeing here is the evolution of what we call the lapse function, which we can sort of think of it as the gravitational potential, right? So we start with the two black holes. So there we have one over there, we have another one, and they are going to merge, and yeah, they merge, and we're left with one single black hole. So yeah, of course, I mean I could be plotting, for instance, the strain of gravitational waves that's emitted. We can just then once we have this infrastructure, we can play around. Other things that one can do, for instance, are neutron star binaries. Now, this particular simulation was done by the group at Georgia Tech, and it's very nice because it's simulating exactly this particular event, so GW170817, which was the merger of two neutron stars. So they set up the configuration such that the masses for each neutron star matched each of the objects. Let me play this. Well, let's at least go through the credits. Again, this was done by the group at Georgia Tech. Let me try to play this again if I manage to find my mouse. Ah, there we go. Okay, so here on the left, we have the matter density, so for each object, for each neutron star. And here on the right, it's the strain, so it's the gravitational waves that are being emitted during this in-spiral. And as they approach, they're going to sort of, I don't know, destroy each other, I suppose. And this is the signal that is emitted, and that was detected by LIGO and Virgo back on Earth in 2017. So again, this is something that you can do with this infrastructure. If we go into slightly more exotic setups, we can do, for instance, dynamics of boson stars. So as Carlos was just explaining, and he showed some evolutions. So this particular configuration, this was done by Pedro Ildefonso, the master student at our group in Aveiro. This is a configuration that it's set up in a way that it has a repulsive, what you can think of a repulsive potential. So these two objects are sort of repelling each other, right? And they continue to oscillate back and forth. So this is, I think, it's very hypnotic, and it's and it's a very interesting and a very nice simulation that, again, that you can also do with all this infrastructure. Another thing that one can do is this thing that I call target practice with black holes. This is a simulation that was done by Zhen Zong at IST Lisbon, and what we are about to see. So this configuration here, it's a boson star. I mean, you can think of this also, if you want, as some lump of dark matter, right? But for these purposes here, this is a boson star, and off came a black hole, right, colliding through, going through this medium. And as you can see, it's completely destroying the star. So let me play it again. At some point, the black hole will come from down here. It's coming at roughly 50% of the speed of light. So there we go. So you can see this is a very interesting configuration. It's an extreme example of tidal locking. And yeah, so the black hole comes, eats its lunch, right, which is the whole of the boson star, and continues along its merry way. So this is, yeah, once again, this is something that you can do with this infrastructure. And yeah, and this infrastructure, it's the topic of the next sessions. So I will just say a few things about this, and since we're a bit late, then I'll probably wrap it up, and then we'll continue tomorrow. But let me just mention the main ideas that I would like you to keep about this toolkit, about this infrastructure. Now, generically, there are a bunch of things that one needs to consider when doing, or when one wants to do numerical evolutions of Einstein's equations. I've separated this so there's a bunch of things that need to be done. I've separated into sets. So there's a bunch of things that need to be done even before one is thinking of, even before one turns on the computer, right? So even before thinking about coding equations, there are a bunch of things that need to be taken into account. The first is writing Einstein's equations as a well-posed initial boundary value problem, okay? So this is related with what I was telling you in the very beginning. So there are different ways of writing Einstein's equations, but we want them as a well-posed initial boundary value problem, so that the solution's behavior depends continuously with initial data. We also want numerically suitable gauge conditions. Now, once we have this, then and only then will we consider discretizing the resulting partial differential equations. Okay. Then we also need to specify constraint-preserving boundary conditions, and we also need to find a way to deal with singularities, particularly, of course, I mean, if we're dealing with black holes. Now, during the numerical, assuming that we have all of this, during a numerical evolution, again, we need to be able to compute constraint-satisfying initial data. So we need to be able to specify the initial state that represents a snapshot of the physical system we want to evolve. Then we need to implement some sort of mesh refinement capabilities so that we can efficiently handle the very, very different length scales that will be present in the problem. Just imagine that we need to be resolving, for instance, on a black hole, if you have a black hole collisions, we need to be resolving to very, very small objects. But we also need to resolve, but we also want to resolve whatever physical quantities we're extracting, in particular the signal in gravitational waves. But there's absolutely no way that we can use a numerical grid with the same resolution throughout. It's just impossible in terms of available memory. So we need some sort of mesh refinement tool. Then, of course, we need to find a way to extract physical results in gauge invariant fashion from the numerical data, and so on and so forth. Now, my point here is that very easily, so let me just go back. So very easily, each of these items, so 1, 2, 3, well, 2 not so much, but so this, this here, each of these items here, I mean, very easily, each of them would take a PhD thesis, okay? So, I mean, if you have a particular, if for whatever reason for your research, you have something that you want to do and you want to evolve Einstein's equations, and you don't have any tool, any such infrastructure available to you, and you decide, okay, I'll just do my own. Okay, that's fine, but once you're at the stage that you'll be able to finally tackle the problem that you wish to do in the beginning, your PhD thesis, or at least your grant, will have finished. So I mean, it really is a bunch of tools that need to be, that are highly non-trivial and need to be, and take a long time to develop. So it's extremely convenient, of course, if you have tools that are already available, that you can then build from, so that you don't need to be thinking about implementing mesh refinement libraries, thinking about the most efficient way of dealing with input and output, thinking about parallelizing your code. I mean, these are all very interesting questions, but they have nothing to do with the physics that you want to be extracting. Okay, so this is what the Einstein Toolkit does for you. It's not the only tool that does this for you, but it's well, it's one that's been available for a long time. It's completely free and open source. It has a vibrant community around it, and yeah, and the goal for the next couple of sessions is to tell you what we can do with this infrastructure. Yeah, this is probably a good point for me to stop, and well, I'll be glad to take any questions, and then we can resume from this point onwards in the next couple of days.
Well, thank you, Miguel, for the first talk, and some questions. So can you?
Hello, Miguel. So why you took so much time from the BSSN formalism till the first evolution of Praetorius? I mean, so much time, like 1 year or something. But what was the thing that was not, that was missing, let's say?
Yeah, thanks. So the thing that was missing, the thing that was missing was the gauge condition, was the moving puncture gauge condition. So it's a bit of back then, people were so afraid of and rightfully so, I should say, people were so afraid of having something that's so singular, a singular point or a singularity in the numerical domain, that they were trying to sort of hide it away, or they were trying to have it fixed to fix it on a particular grid location, and then just find a gauge that would, you know, do around that, right? Now this was creating all sorts of problems, because the coordinates would get extremely distorted. So basically, because of the reason that you would imagine. So basically, you would then have like a couple of points that would be fixed in a numerical grid, but the black holes themselves would of course be moving around. So the coordinates would be extremely distorted, and this was not working properly. Yeah. So once this was sort of a mental block. Once this was relaxed, magically things started to work. I mean, it's a bit more complicated than that, but this is the idea behind it.
So, any more questions?
Thank you, Miguel, for the nice introduction. So I was wondering about you mentioned that one of the evolution we will do it on your our own laptops, but how computationally expensive is it, or?
Yeah, so the answer, as usual for these things, is it depends. But the thing is that for modern laptops, for a typical simulation, say of an in-spiral of two black holes, a modern laptop can do it without any problem. This was not the case some years ago, but these days a modern laptop can handle it without any problem. Now, of course, at least in terms of requirements. Now, depending on how much resolution you have or how many orbits you need, you may have your simulation running for a long time. I mean, a week maybe. So then you would have your laptop just doing that simulation for a week. You can't do anything else. But a modern laptop can do it.
But we won't stay here.
No. I'm going to provide already with the data.
So, but for head-on, it's much less.
Yeah. For a head-on, this can work in maybe. I mean, it depends on how far apart they start, but this can be done in a day.
So I think if anyone has another question, let's wait tomorrow for that. And so let's thank again Miguel for the talk.
So again, just remember, so for those that would like to follow the hands-on session, to download the virtual image, okay?